We're going to talk a bit about multimodal settings and in particular moving into how to, let's say, try to generate data where we assume that we have multiple sources of information about, let's say, some objects. And this could be audio, it could be images, could be some textual description about, let's say, a person. But at inference time, when we want to do some downstream task, classification, something like that, we are missing one or more of these modalities. We have them in train time, but we are missing one or more modalities at test time. So this is the setting here. We will see that we propose to attack this problem kind of through neural networks, so deep learning. We will have to set up some kind of cost function to try to be able to generate these missing modalities. We will also assume we have available labels, so this is a supervised setting, and we would like to do classification also in the end. So we need some kind of cost function based on some theory, of course, to guide us towards the solution. So here we will see that the engine, the underlying engine, when it comes to this data analysis, will be variation autoencoders. So variation autoencoders are... Yes, please. Yes, thank you. Variation autoencoders are encoding, decoding structures, and encoding and decoding are basically performed by neural networks. Variational, we'll see that this is connected to what Michaela van der Schaar talked about in the previous tutorial, where she talked a little bit about implicit, so-called, likelihood models. So this is this setting. And I could also just mention that it's sort of a bit concrete because it's based on a particular paper that was just published like very, very recently in the journal Neural Networks. Good. Okay, so let's try to motivate a little bit the setting. It could be motivated from many, many different viewpoints, but I should also mention that Rogelio has an interest in finance. So now he works as an associate professor at the business school, Norwegian Business School, which is in Oslo. But he also, in his PhD, was actually associated with Santander Bank, so he has this interest in finance. So therefore, our motivating example comes from basically the bank world. So let's say that, you know, when banks loan money to people like us, there's a risk that we can't pay back the loan. So this is something that people like Rogelio are very interested in analyzing, of course, the risk of loans not being paid back. And then apparently, like a new thing in this bank world is, in addition to, let's say, the sort of regular data about customers, like your income and these kind of things, when trying to predict whether you will default your loan, is to go into this kind of database, which is international, but where you have this kind of textual data. So it's called, I need to read a little bit on my screen because I don't remember the exact name, Management's Discussion Analysis section, yes, Form 10. So this is available to the banks. It's basically a text description that can be associated with customers like us. However, not all companies are obliged to fill out this kind of information. So the idea here is, in this finance world, that sort of in training time, let's say, when you set up your models, you have available this kind of regular data about persons like us, but also this text data. But then in test time, you may not have this text data, then it's missing. So this was a motivation, at least for Rogelio. So you could say that in general, we are what's called in the multi-view setting or multimodal setting. So you could think about what I said in the beginning. Let's say images, text, audio from me, for instance. That would be this kind of multimodal setting. And the idea is we hope to exploit all of these modalities. So the idea also here is that we are in a classification setting. So let's say that one of these or more of the modalities are missing exactly when we need it, when we need to take some decisions. And can we classify even if one or more modalities are missing? And also, in many cases, it would be of interest to try to generate this one, or let's say two or more, modalities that are missing. So that's the generative part. Okay. As we move on, we will talk a little bit about how to think about a framework to attack this kind of problem. This will lead us into variational inference, implicit likelihood modeling, basically. And then we move a little bit into the specific setting of this particular paper, which is an instance of generative models in the variational inference setting. And then we close with some examples, some results. All right, so again, when having multiple parts of information about the same object, then the underlying idea here is that, for instance, when I say something to you, and if somebody took a picture of me at the same time, then there's something here underneath, kind of me, that generates both the picture taken and the audio. So there's some kind of latent variable that sort of generates both the picture and the audio. And there could be many more pieces of information or modalities, of course. But the idea is that there's something underlying the latent variable that we will often call Z that generates what we observe. So this is kind of the underlying idea behind all of this. And you can see here that, for instance, in this particular figure, there's this latent representation. You could think of the colors here as just describing particular, like objects in a way. And the objects in this case would be digits. And then we could have what we observe could be different images of the digits, in this case, two particular different ones. And it could also be just like a text string that says 6 or 3 or 1 or something like that. So in this case, we will have 3 modalities. But they are generated from the same latent variable. Then, of course, you could also think about going sort of the other way. You observe something, let's say 2 modalities, that's the x1 and the x2. Any way to infer what this underlying latent variable is. So that's now this kind of Z, which is here colored as part red and part blue. The idea is that this is a shared representation for whatever modalities we may have, 2 in this particular sort of illustration. So this is a setting. So now we just think about some observed vector, x. And this is now sort of taking one step back. Okay, so now we're just going to say a little bit about variational inference, just a general framework, which we will use then in our multimodal setting. So one step back. Okay, let's now just think a little bit simpler, easier. We have something observed, that's x. And we have this underlying latent variable in this case for the one observed x, and it's z. And then what we would like to do is basically in likelihood-based inference to optimize our log likelihood function. So now you could basically conditional distributions will be very, very important here. We have the latent variable, we can observe x, so we have some distribution x given z, and also the other way around. But if we're talking about our log likelihood function, log p of x, so this is now just back to the basic setting, we want to maximize log likelihood, then we end up in a problem because we know that we have to consider the latent variable. Right? It's there, it influences x. So whenever we observe x, it's because some z have generated x, basically. So then we need to consider x and z jointly. We end up with the joint distribution, going from the joint distribution to the likelihood function, which is p of x in this case. It's very, very difficult. We have to do this integral, in theory, over all of z, the Latin space, and this is intractable. So this is sort of always what becomes the key challenge when you're talking about latent variable models. So you could envision having to integrate over this whole space, and it's just not realistic the way it's phrased here. So that means that if we have x, we want to go to z, that also becomes intractable. We need to do something else. So what we basically then think, so now we have colored here, p distribution z given x is because it's important. In variational inference, what we would do is, we're interested in p of z given x. We introduce what's called a variational distribution. So that's q. So it will now sort of be a proxy for p of z given x. And we will use this as an approximation. And we will go through some steps in the next slide, don't worry, about what this elbow thing is. But the thing is that when we introduce this sort of helping or proxy distribution q, which we typically choose, we say it has a particular parametric form, and in the end we need to find parameters of this q. We have basically chosen the form of this distribution ourselves. Then we can show that, and we will do that in a second, that the log likelihood has basically a lower bound. So the log likelihood is intractable, but we can formulate this lower bound, and then we can try to optimize the lower bound instead as a proxy. So this is why it's called implicit log likelihood, as Michaela mentioned, actually. So now you can think of already, this will be what we call the elbow, which is this lower bound. Evidence lower bound is the acronym. Evidence is sort of the name also for the log likelihood. That's why we call it evidence. Now we can already think of this p of x given z here, that you can see. We will go through some steps, but you see a p of x given z. You can already start thinking of that in terms of a neural network. So this will be our decoder in practice. So you can see that what the elbow says is that we need to reconstruct well from z. We generate x. And we want this to be good. This is the first term. And then the other one, it basically says that this proxy distribution q, z given x, we want it to be close to some prior distribution for our latent variable, p of z. So the KL here means the Kullback-Leibler. Where does this come from? Let's try to look at this. So we will do this step by step. To be honest, I always need to do this step by step because if 2 days goes by, I forget all of these steps, I have to redo it. So we start with the log likelihood, that's a starting point. And we already looked at this thing here, right? We have to integrate out the z to get the p of x. And now the thing to do is sort of to do a trick. And that is to just, where is the pointer? Let's see. Yeah, not sure if you can see this, but this basically says that we do a trick, we do nothing, but at the same time we do something important. So we introduce this fraction, thank you, where we introduce Q. This is our variational distribution I mentioned previously. So we do nothing, but we do something actually. Then I just colored Q here in red. And this is because now we realize that we have integral, we have Q, Z, and we have a dz. So actually it means that the other things here, they go into an expectation with respect to this Q. This is a definition for an expectation, integral, something, distribution with respect to something, d of that something. So that is the trick now. We see that we have reformulated the log likelihood into an expectation over this variational distribution that we basically introduced ourselves, this Q. Now we see that we have a log, because we started out with the log likelihood. And now we use what's called the Jenssen-Shannon inequality. So whenever you see something like this with a log there, then you can change the order of the expectation and the log, and you have the greater than or equal. So this is by the Jenssen-Shannon inequality. This is a bit important because this is what will lead to the so-called Kullback-Leibler. Exactly this trick. All right, then we are here. We see that we have a joint here. We do the base stuff, you know, where you can reformulate any joint in terms of a conditional and a prior, either in the form x given z and then p of z, or the other way around. Now it's useful for us to do it this way. So next step, we have equality going from here to here. So now we are not doing anything. We're just sort of rephrasing things a little bit after we do base here. And then we get this p of x given z, which I mentioned. This you can think of as a decoder. And then we have something here. We have still expectation. So now we have two terms. We have expectation. We move expectation inside each of these terms. And we get the two expectations. We have not done anything wrong by doing this. And then actually this expectation here, you can again envision this integral. And then we have something q of z given x, p of z. It's the expectation here, and actually it's the definition right here of what we call the Kullback-Leibler divergence. So the Kullback-Leibler divergence is super duper well known and used everywhere and so on. It's a measure of distance basically, not metric distance, but a form of, let's say, distance between probability distributions. So, since we did the Jenssen-Shannon up here, that's why we get a lower bound. And basically, we have our sort of reconstruction term here. And we have this, you can think of it as a regularization term. And this is the elbow. This will then be our cost function in practice. This is what we try to optimize in the end. Can just sort of, if you're interested, you know, you can read about this many places. For myself, I found it quite useful to go to this guy, Bernstein, and just, you know, read a little bit about these things. So anyway, that's just a small suggestion. How the elbow, the evidence, the Kullback-Leibler, all of this interplay goes together. But in the end, the starting point is the log likelihood function. It is the intractable situation we are in. We introduce the variational distribution. We can then formulate a cost function, it's the elbow, and then of course we need to do something, we need to optimize it. How do we do it? Optimize with respect to what? This is when the neural networks come into play. So now we will use the elbow cost function, but will be what we call an autoencoder, encoder-decoder network kind of structure that will do the job of actually setting up an optimization framework. And then something strange here occurs. So why did I sort of now suddenly write elbow as a function of this mu sigma? Mu with respect to the p, mu with respect to the q, which is our variational distribution. It is because we'll parameterize the distributions p of x given z by a neural network, q of z given x by another neural network. The q part will be the encoder, yes, and the p part will be the decoding step. So this is still just basic sort of stuff, but just wanted to mention this before jumping into our particular sort of formulation for setting up the elbow in our missing modality framework. All right, so now you see here that the Q I mentioned, we actually select basically the parametric form of this variational distribution very, very often. It's a Gaussian. We will do that too. And what the neural network does is to sort of predict or give us, try to find reasonable mean value mu and sort of variance or, covariance matrix in the multivariate case for this. Could be a very, very big neural network that now basically parameterizes this Gaussian or normal distribution Q. This is doable because we can now sample. So this is connected to what's called the reparameterization trick when it comes to how to make this actually work in practice. So we, in the latent space, the Z space, we can basically inject a little bit of noise, kind of, that will trigger the sampling of Z. That's what you can see here. This is important to make the whole system of these neural networks end-to-end trainable. We can use backpropagation and so on. You can go a little bit into the literature, on the details of the reparameterization trick and so on, if you feel like it. Not intending to go more in details on this right now, but you can think of the Q now as a parametric form distribution. It's in the latent space. It's Gaussian. And then we will also, of course, have to make a choice on this prior P. It will also be Gaussian in the end, and then we will make them close. That's the idea. Okay, so this is still to try to show the same thing, just by showing you the bell-shaped curve of the Gaussian to sort of show you that the idea is that what the neural network does is to give us basically sort of mean and variance and the shape that we have chosen. Could be another shape, but of course Gaussian is something we like to work with. Okay, so that was a little bit generic. In our particular setting, and it should also be said that it's a very active field of research from the basic setup of the variational autoencoder, which has been super important. I mean, you will see this framework from, I think, something like 9 years back, maybe, the first papers appearing, variational autoencoders. Very many places, but multimodal setting is development in this kind of theory, and it's not without challenges. And also when it comes to missing modalities at test time, this is a bit new. So in our setting, what we assume is that when we train our system, we have all the modalities present. That's XO. At test time, we will have our kind of a situation where we may be missing modalities, but we also assume that we have labeled. We are in a supervised setting. That's why you see the Y here. Right? So we have labeled multimodal data. However, downstream task, we are missing modalities. And also there, should say it's important, there we are, of course, doing classification. We don't have then label available. It's like a standard supervised setting. In training, we have labels, we can use them. And then, of course, in inference time, we don't have them. And not only classification, I also mentioned, actually to use the generative property of variational autoencoders to try to generate the modalities that we are missing at test time. So two aims, both actually to just, do classification, but also to generate missing modalities. Then it should be said that when it comes to this particular setting, there are some additional challenges, actually, that we build upon some recent literature that are present. We're not going to go into all the details here, but we will see a little bit of it. It has to do with mutual information. So, this is a problem, actually, that in the end means that even if we have multiple modalities, it could be that in our latent variable, we are not able to capture information from all of the modalities because of this challenge of mutual information. We will now discuss that a little bit. So now we have moved away from the generic setting. We're now in a more particular setting when it comes to missing modalities and generative models. Right, so as mentioned, we're not going to try to go too much into the details here. But it can be shown, we have shown, building on other people's work, that when we, in our particular setting, where we have multiple modalities in train time and also the labels, we set up the elbow, then we will have some conditional distributions. It will not just be an X and a Z, but it will be X observed and XM and Y. But everything is basically the same, just with some new variables. Then it can be shown that in this setting, the KL that we discussed, which is a part of the elbow, and this is just that part reformulated in our particular setting, inside here, it can be shown that this KL divergence upper bounds what we call mutual information between what we observe and the XM here that we have sort of in test time, and then this latent variable. And this is not good, because the whole idea here is that we want to sort of take what we observe and we want to sort of transfer information about what we observe to this latent variable that we try to learn, and also to generate the missing modalities at test time. And if there's a component within our framework that inhibits transfer of information from what we observe to the learning of the latent space, which is supposed to, have information about all the modalities, and then also inhibits generation of missing modalities at test time, then of course that's not good. So then you could probably ask, so why did you use this elbow framework in the first place if it's not so good? We don't really know any other way at the moment. So then the idea here is we have what we have. We have the elbow in this particular framework. But there's a component within the elbow which is not good for our purpose. So what do we do then? So we kind of have a situation where, let's say, mother or father says to you, you're not allowed to buy, like as many ice creams as you want to. There's an upper limit from your mother or father. That's not good, of course. So what do? You go to your other parent, and you hope that your other parent says, there's no limit, just do whatever you want to. So what we do here, we know that there's a component, mutual information. We know it's there, sort of hidden within the elbow. It inhibits us. So what we say, okay, let's introduce another term which just does the opposite. It tries to nullify the bad effect of the mutual information term. This is what you can see here, actually. We have our elbow, and then we add this term, which we know is hidden inside here, to counter the bad effect of mutual information. So it's like going to your other parent when your first parent says no. And then we reformulate a little bit this whole, elbow plus this new term. This is sort of our new contribution. Okay? And then we have to, of course, deal with these. We have neural networks, and how do we estimate these Kullback libraries and all that stuff. And one of the Kullback libraries is sort of easy, because there we have chosen Gaussian assumptions, and we can actually analytically give you a mathematical expression for the Kullback library in that case. But another one is more tricky, and we won't go into the details. We'll just tell you that one of these Kullback libraries will be estimated based on samples, not analytically, but based on samples. This is part of the reformulation, actually, to show that we can estimate this thing. Not going to go too much into details here. Can just say that if you ever heard about something called maximum mean discrepancy, which is what we call a kernel-based method, like a two-sample test. Actually, Michaela touched upon this super briefly without actually mentioning it. It is what we use, actually. So we use this thing called maximum mean discrepancy to give us an estimate for a Kullback library term, which is connected to a mutual information term. This goes into our cost function. It can easily be computed, and we use it. In the end, this is our architecture. Then, of course, there's a whole optimization procedure. We have to choose our particular layers, how many neurons, all of these things, of course, we have to choose. In the end, we have a path here where we have our, all of our available information. We have basically a decoder part here that takes latent variable, what we have observed, try to generate, and then we have a reconstruction term in our elbow. Okay, that is part of the optimization. So this is how it goes, kind of, that we observe, we have labels to, we encode Z, we go out again to our XM, we reconstruct. It's all in an optimization procedure from the elbow plus this mutual information term we introduced. At test time, then we don't have certain modalities, right? Then we only have this, whatever we observe, maybe 2 out of 3 modalities, or 1 out of 5 or something. And this is the only thing we have now. We don't have any labels Y either. So at test time, we use this, what we have. And then we have a certain sort of neural network gives us the latent variable Z. And this goes into this neural network, which we have found during training. And from this, we basically generate. And this is our classification at test time. So there's a lot of stuff behind here that we won't discuss all the details, but hopefully that's sort of the main steps. So, before we go into now just sort of the final part, neural networks, we have autoencoders. They are generative because in this particular case, we are talking about what we call the variational autoencoder setup. It means, in practice, that we have to formulate the elbow. So implicit likelihood-based optimization problem. Then we are just introducing a particular problem setup where we have this missing modalities at test time, but in train time we have observed everything, and we also have labels. It's called conditional because of this conditional mutual information term, by the way. And then we can actually try now, of course, to train our system based on some input data, try to generate data, see how well it does, and also classify. Right, so now this will not give you too much sort of information. This is just to show that there's a comprehensive set of experiments, because there are other methods that try to do similar things. But in our case, we have different data sets here. And this is us in the end, but I think it's more informative to just go here. So now we're talking about the generative capabilities. So now you can think of train time. We have 3 modalities, descriptions for every digit in this case. We have the written thing here. We have an image. This is MNIST, basically. And then we have SVHN, which is this kind of more difficult pictures of digits. So we have this. We also have label for which digit we are talking about in train time. And then the idea is that, okay, in test time, one of these modalities will be missing. And then we want, for instance, here, in this first example, we just get this at test time, the textual description, and we want to classify well, and we do well, but we also want to show that we can generate the missing modalities, which are these 2, and these are generated. So both of these guys are now generated by neural networks. This is the same example, basically. Now we assume that at test time we have 2 modalities available, and we generate these. And if you look a little bit at sort of the, let's say, available or sort of true SVHN images, you will see that this is not too sort of far away, at least visually, from what you would expect. And this is corroborated in some experiments, quantitative experiments, and so on. This is generating image tags. So now this is a generative property to generate tags based on only having the images at test time. But in training time, we had both available tags and images. And of course, it's difficult to say whether one thing is much more reasonable than alternatives. I guess it's a bit up to you. But in any case, you can see that for this particular image, for instance, our method says sign and fisheye, and we have these alternatives for the other methods. And then you can see similar things here. So like on this, for instance, maybe not too strange, at least. And to be honest, I don't know what A700 actually means in this case, but that's what come out of this alternative. Okay, so this was to show you a little bit as emergency replacement for Rogelio, variational autoencoders, hopefully the fundamental concept of intractable log likelihood, what do we do, elbow, how it works, particular setting, which is very modern, multimodalities, missing at test time, do classification well, hopefully generate well, so that's new. It has to be said that it's not only the setting which is new, but it's also the way, of course, that we perform by having this counteractive component in terms of mutual information inside, in addition to our elbow cost function. Okay, but that's a bit specific to this particular problem setting. Should also be said that in this particular paper, we also show that this is helpful when it comes to this problem, which is called posterior collapse. It's sort of, for many, some of you may be aware of this, where in the latent space you kind of have dimensions that are just not contributing at all. So we show also that this is helpful to counteract that. We can also show that this mutual information term is actually doing useful stuff, quantitative examples on that. Which is a bit specific for a tutorial, this particular setting with the missing modalities and so on. But the framework behind it, variation autoencoder, elbow, that's the generic part. Okay, so I think that I will end there.